Alright, so this next video for Math 1560 Calculus 1 at U of L for fall 2017, we're going to use the method of U substitution introduced in the previous video to integrate the 6 trigonometric functions. And 2 of the 6, of course, we already know how to deal with, sine and cosine, because things are quite simple there, right? The derivative of sine is cosine, the derivative of cosine is sine, and so I can always take this minus sign and I could move it over to this side. So if I wanted an antiderivative for cos, well, the antiderivative for cos I just move in this direction. The antiderivative for cosine should be sine, and again, if I wanted the antiderivative for sine, I read right to left, and the antiderivative for sine should be negative cosine. So those two I get straight away, right? I get that the antiderivative for cos x, or the indefinite integral if you like, the integral of cos x dx, is sine x plus c, and the integral of sine x dx is negative cos x plus c. Okay, but what about the other 4 trig functions, right? You know how to take the derivatives of tan, secant, cotan, cosecant, but the antiderivatives, we notice that none of those functions show up on their own as the right-hand side of one of these derivative formulas, right? I get secant squared, I don't get secant. I get secant times tan, I don't get secant by itself or tan by itself. So if we want to get antiderivatives for the other trig functions, we're going to have to be a little bit more clever. Okay, so here's the first one, antiderivative for tan. Complicated looking, right? That's a natural log. Natural log of secant x plus c. That's the formula for the antiderivative of the tangent function. How do we come up with that? Well, how would we do this if we knew nothing else? Well, remember that whenever you're working with any of the trig functions other than sine and cosine, and you don't know how to proceed, one of the steps you can always do is you can write them in terms of sine and cos and see if you spot anything. Okay, so what is tan? Tan is sine over cos. Now I want to tackle this with a U substitution, so I see, okay, I've got a sine, I've got a cosine, and the derivative of sine gives me cos, the derivative of cos gives me sine, and so I've got 2 choices I could make for my U substitution, right? And so I could say, oh, well, what about sine? The derivative of sine is cos. I've got that sine sitting there. Do I want to let u equal sine x? Well, think about what happens if I do that. Then du is cos x dx. But I don't have cos x times dx, right? This cosine is sitting in the denominator, not in the numerator, right? It's not multiplying dx, it's dividing dx. So that doesn't work. So this is no good. I can't make that substitution. It's not going to work out for me. So if that doesn't work, well, then we try it the other way around. So let's try u equals cos x. Well, then du is minus sine x times dx. Move that minus sign over. Sine x dx is minus du. And now I'm in business because I have sine x dx sitting right there. And 1 over cos is just going to become 1 over u. So what I get is 1 over u times minus du. So I can pull the minus sign out. This becomes minus the integral 1 over u times du. And we know how to deal with 1 over u, right? 1 over u is the derivative of log u, or log absolute value u. So I get this. I get minus the natural log of u plus c. Okay, and then we substitute back in minus the natural log of cos x plus c. Okay, now we could leave our answer like that, and that's a perfectly fine way to write the antiderivative for tan, but that's not what I have up here. Right here I have log of secant x. Well, how do I get that? Remember that the natural log of 1 over a number, well, that's the natural log of a to the minus 1. That's minus 1 times the natural log of a. So kind of going backwards, if I have a minus sign out front, like this minus sign, all right, I can bring that minus sign in and it becomes an exponent, right? If I bring the minus sign in, it becomes a minus 1, becomes a reciprocal. And what's 1 over cos? 1 over cos is secant. So I get the natural log of secant x plus c. Okay, and then we're done. And so I'll let you guys do the one for cotangent. It's going to be the exact same sort of procedure. So if you follow the steps that I just did for tan, you'll be able to get the corresponding integral for cotan. Okay, so now we've done 4 out of the 6. We've got sine, we've got cos, we've got tan, we've got cotan. What's next? How about secant? Now the one for secant is kind of scary looking, right? Natural log of secant plus tan and then plus c. This is quite a complicated result, and this is one that took people a long time to figure out. For the longest time, nobody knew what the antiderivative for secant was. And there are various other ways that you might try to come up with this, and there were different tricks that people tried, and then somewhere along the way, and I don't remember who kind of came up with this trick the first time around, somebody noticed kind of a clever trick. They said, okay, secant x is the same thing, so what I'm going to do is I'm going to multiply by secant x plus tan x. I'm going to divide by secant x plus tan x. And why on earth would you do that? Well, I think maybe someone spent long enough staring at these derivative formulas, and they said, okay, the derivative of tan, secant squared, well, that's secant x, and maybe they noticed that the derivatives for tan and secant have a common factor. Both of them have a secant in it, right? The derivative for tan is secant times secant. Derivative for secant is secant times tan. Well, what if you started with the sum of the two? What would you get if you took secant plus tan and then you took the derivatives? Well, you would have this common factor of secant left over at the end. And so let's see what happens. So we make this kind of trick. We do this trick, and now we're going to actually multiply through the numerator. Secant squared x, secant x, tan x, dx. And on the bottom, secant x plus tan x. And okay, now that u substitution is staring us in the face, if we let u equal secant x plus tan x, then du becomes secant x tan x, there's the derivative of secant, plus secant squared x, derivative of tan, times dx. And so this becomes simply 1 over u times du. So that's the natural log, absolute value u plus c, and we substitute back in secant x plus tan x plus c, and we're done. Okay, that takes care of secant. I'll leave you guys to tackle cosecant as an exercise, and it's going to be the exact same procedure with some different choices along the way because you're dealing with cosecant. And I've given you the answer, so one thing you could always do is work backwards from the answer. That's going to give you a pretty good hint at what you need to multiply and divide by to get things to work out for this cosecant function. Alright, so that's it for the trig functions. We're going to move on. We're going to do one more video on substitution. We're going to look at how to tackle substitution in a definite integral. Oops.